terminology and we will start our balancing chapter. First of all, we have to understand what the balancing is. So let us move the study for this introduction. We have the first diagram in our case. In our case, there is a shaft and mass m is attached with this shaft at a radius r towards upside, as you see in this diagram. So here in this diagram, if you see this, what will happen? The system will rotate with omega angular velocity. If it is rotated at omega angular velocity, the mass which is rigidly fixed towards the system, it will also rotate with omega angular velocity. And how much centrifugal force is generated? M omega square r. Now I think this is clear for you. Let us assume another system. The system has a shaft, there is a rotor. So instead of a single mass, what we consider? A bunch of a mass. So here there is a rotor. Now the rotor is having eccentricity E. Now what is the eccentricity? It is none other than the radius. It will represent the CG of a system. Okay, center of gravity. Yes, the CG of a system. So it will represent the CG of a system in our case. Then what will happen? If the rotor is rotated at omega angular velocity, the shaft is rotated at omega angular velocity, the rotor itself rotated with omega angular velocity, and because the CG is slightly deflected, what will happen? The total force of the system will not lie on the axis of the shaft. It will lie on this rotor CG. Okay, and by this system, what will happen? The system will be banded. The shaft will be banded. Okay, now we have to balance the system. So what we will do to balance the system? We have to manage that the axis of rotation, the CG of the system, I repeat, the CG of the system should lie on the axis of rotation. The CG of the system should lie on axis of rotation. Okay, and the second term is we need to balance the system as we need to balance the mass. It means if there is greater mass towards upward side, we have to put the another mass which we need to balance. You know the seesaw. What is in the seesaw? There is right hand side and the another side, left hand side, there is your friend. And what will happen? You need to balance the system. Okay, likewise, if both the systems are on the same plane, they are on the same axis, they are on the same line, and if the system is having the next point. Okay, now this is like the static balancing. Let us have the static balancing. As you remember the seesaw example, if you are at the right hand side, if your friend is at left hand side, and the distance between both of it is similar, and if any one of you is heavy, that seesaw will be bended towards that direction. Okay, now if we need to balance it, what we have to do? We have to reduce the radius or we have to reduce the mass. It is just applicable in our system. As you see in our chart, what is the static balancing? For the static balancing, if we need to balance the system, the resultant force or the effect of all the forces should be on the axis of a shaft. It means the axis of a shaft will remain steady. The axis of a shaft should have the all forces. Okay, next one. The center of gravity should be on the axis of rotation. It means there should not have any kind of fault in the system. Next one, the combined mass system should also have on the rotation of a system. It means we have to do the statically balanced system. As you see in our previous slide, there is, as you see this in our previous slide, what is in it? The mass is at radius r. Okay, and this system is imbalanced system. What we do for the balancing? We have to put the same mass, or the different mass, same or the different mass, same or the different angle, and we will get the total balancing. It means M1R1 should be equal to M2R2 in our case. Okay, so now this is for the static balancing. The prime value should be the force F, sigma of all the forces. sum of all the forces should be 0 with respect to the static balancing system. Now next is a dynamic balancing system. For the dynamic balancing, in this dynamic balancing we need to consider all the forces which are rotated, all the forces by which the system is rotated, and all the moments which are created by the forces. It means for the system, what we have to do? Forces should lie on axis of rotation and sum of all the moments of all these forces should be 0. So, for the dynamic balancing, what is the prime value? Sigma of force F should be 0. Sigma of moment should be 0. So, force should be 0 as well as moment should be 0. So, for static balancing, all the forces, sum of all the forces should be 0. It should be balanced. And for dynamic balancing, forces 0 is the primary condition. For the dynamic, couple or moment should also be 0. So here, this is the introduction of static and dynamic balancing. Now let us have the types of balancing. Types of balancing, we are having two types of balancing. One is a rotating mass system and second one is the reciprocating mass system. And we will say balancing of rotating masses and balancing of reciprocating masses. So here in our case, let us study about balancing of rotating masses itself. So here, let us study about balancing of rotating masses rotated in a same plane. Now, do you know what is the same plane? First of all, it is having two methods. One is for the graphical one and second is analytical one. We have to study the graphical method itself. So let us have our graphical method. For this graphical method, we have one diagram as you see on the screen. So here you can see OX axis, four different masses, M1, M2, M3, M4. Clear? Mass M1 is at theta 1 angle from OX axis. Mass M2 is at theta 2 angle from OX axis. So all the masses, all the angles we have to consider with respect to the base axis. It means OX axis. And we will say this OX axis as the axis of rotation. It means we have to study all the angles, all the forces with respect to the axis of rotation. Okay? Now, let us have mass M3. So, mass M3 at theta 3 with respect to OX, so as M4. Clear? Now, next, you have to understand that in this case, I didn't mention the radius R, but just assume all are having different radiuses. It means R1 for M1, R2 for M2, R3 for M3 and R4 for M4. So it is having four different masses, four different radiuses and four different angles. Clear? Now let us have our next topic. In this case, what we have to do? First of all, we have to calculate centrifugal force. Now, as you know, what is the value of centrifugal force? M omega square R. If mass is M1, radius is R1. What is the centrifugal force? Exactly correct. M1 omega square R1. If M2 is a mass, R2 is a radius. What should be the centrifugal force? M2 omega square R2. Same as for mass M3 and R4. Now, in this case, omega is same for all the masses. It means for M1, for M2, for M3 and for M4. So all the masses, for all four masses, angular velocity is same because they all are mounted on a same shaft. Okay, so if all are mounted on a same shaft, if the rotation of a shaft is omega, what should be the angular velocity? Angular velocity is same for all the masses. Now, for our sake of simplicity, what we have to do? We have to neglect that omega square value in our calculations. Okay. Now, if we neglect omega square value, what should be our centrifugal force value? M1R1. For the second force, M2R2. Third force, M3R3. And fourth is M4R4. So here we have to draw the value according to M1R1, M2R2, M3R3 and M4R4. Yes, the product of mass and radius itself. Right now we have to omit omega. Okay? Right. Now let us try to draw this diagram. So let us have the graphical method. First of all, we have to draw the baseline and we have to mark theta angle theta 1. Now we have the product of M1 R1. First of all, we need to convert the M1 R1 product in centimeter. Okay, suppose we have M1 R1 as 3 kg meter, right? If R is in meter and mass is in kg, we have to convert it in centimeter. So first of all, we have to take a scale. So for this scale, what we need to do? We need to do 1 centimeter is equal to 1 kg meter. Okay, so let us have to draw in a centimeter. So we have to draw the vector of FC1 in the angle direction theta 1. So this is our FC1 value. You have to draw with me, then and then you will get the exact answer as I have. Now next, we have to again draw the baseline as well as theta 2. Now you know where it is mass M2? It is at 90 degree. So we have to draw M2 R2 value. It means some kg meter. Suppose it is 4 kg meter. So we have to draw 4 kg meter line in the theta 2 angle. Next, we have to draw the baseline and theta 3. So by drawing this, we will get the value of M3 R3. We have to get the value of M3 R3 and we have to draw FC3. Okay. Now then, we have to mark baseline as well as we have to mark theta also, and then in the theta 4 line, we have to put the value of FC4. Now see in this case that this polygon is closed. It is not closed, it is open. If it is open, then the resultant force will give us in this direction as we see. Okay. So here in the upward direction, I represent 2 arrows. One for the resultant one for the balancing one. Now in this case, the resultant one, as we all know how to draw the resultant, in the opposite direction. It means all the forces, the combination of all the forces will have the effect in the upward direction, and this force is in a second quadrant. If you see from the baseline of theta 1, so it is at the second quadrant. This will give us the resultant force value of all these forces. What we need to do? We need to balance all these forces. Now, we have to draw the same line, but the arrow should be at the downward direction, opposite to the resultant force. Okay? So here, we will get the downward direction arrow, and as you see the angle representation, from the baseline of FC4, from the baseline, what we have to do? We have to mark 0 to the angle. It means if resultant is in a second quadrant, we will get balancing force in a fourth quadrant. Balancing mass is always opposite to the resultant mass. Okay? Balancing force is always opposite to the resultant force. And then we will get the value of balancing masses. Okay? So here we will get our values. Now, according to our system, as you see in this case, we have to draw the vectors. So if we draw the vectors from end to the head, the another vector will be started from the head itself. It means suppose FC1 is having the head at theta 2. Okay, so that FC2 will be started from the head of FC1. Same as FC3 will start from the head of FC2. And then if the polygon is closed, the system is balanced. If polygon is open, system is imbalanced. And if the system is imbalanced, we need to balance it. Clear? Now, in this step, what we have to do? We have to measure the length of that dotted line. That dotted line will represent resultant and balancing force. Okay? Resultant in a second quadrant and balancing in the fourth quadrant. We have to find out the balancing one. So here we have to consider the fourth quadrant component. Okay, fourth quadrant vector. Now measure that. Because we draw all this diagram in centimeter, we will get the value in a centimeter itself. Okay. Now what is our scale? 1 centimeter is 1 kg meter square. So we need to convert this centimeter in kg meter square. Suppose we are getting 5 kg meter square, so 5 kg meter as our answer. Okay. So 1 centimeter is 1 kg meter. 5 centimeter is equal to 5 kg meter. So we will get this 5 kg meter as our answer. Suppose in our case, if we know the radius of balance mass, where we need to put the balance mass, if we know the radius, what we can do? Balance mass FCB, balance force, is equal to, our answer is 5 kg meter. If we know the radius R, FC is M into R. If we know the radius R, we will directly get the value of mass M. Okay. This is for the graphical method of our system. Thank you, student. If you have any doubt, you can call me, you can put a message, you can send me the query, and I will give you this basic answer of all our system. If you like this video, you can like, share and comment on this video. It will help me to improve, and it will definitely